Good morning, this is Christina Long and this is the Science 411. This morning's video is over chemical kinetics and thermodynamics, and it's really part one of an overall equilibrium unit, but today we're just dealing with kinetics and thermodynamics. What are they? Alright, so kinetics deals with the rate of reaction and how quickly a reaction occurs. So the biggest thing that you need to look at here is that term rate. Anytime you're dealing with the term rate, you're going to be dividing by time. So kinetics is dealing with how fast a reaction can occur. And then thermodynamics involves changes in energy that occurs in reactions. And the energy really that we're dealing with is given in the name. It's not always going to be heat, but in this case we're dealing with the form of energy that is in heat. So there's something called the collision theory, and collision theory basically is what are things that make a reaction rate increase by increased collisions of molecules. And it's measured in moles of reactant used with unit time. And another way to say it is moles of product formed divided by unit time. And that's probably the easiest to look at. It's either going to be how quickly are you using up your reactants or how quickly are you making products. There are a few things to be considered. Number one, frequency of collisions. The more collisions you have, the faster the rate. Now, it can't just be any collision, they have to be effective collisions. And with that, you've got to have proper orientation. And then you also have to have enough energy for those collisions to stick. Essentially, you're running molecules into one another, and in order for them to react, they have to have the proper orientation and they have to have enough energy. So some other things that affect rate. The type of substance. The ionic substances react faster, and that's because their bonds require less energy to break. So in this double replacement reaction, you've got silver 1 nitrate and sodium chloride, and then it's going to make your silver 1 chloride, which is a solid or a precipitate, and then your sodium nitrate. And the solution, in the solution, the ionic solids dissociate into ions, which means that they're going to break apart into ions, and you've seen this when we dealt with redox and net ionic equations. Those substances are going to break up into 4 ions, and they're going to do it fairly quickly. In covalent reactions, they're going to react more slowly. The bonds require more energy to break. You've got your diatomic hydrogen and then your diatomic iodine. What's going to end up happening there is the bonds have to break and then be reformed, so this is going to take a little bit more time. So in general, type of substances, ionic is going to react faster than your covalent. Some other things that affect reaction rates. Temperature increase. Average kinetic energy increases and the number of collisions increase. Reactions have more energy reactants have more energy when colliding. This increases the rate of reaction. So if you're looking at the picture on the bottom left, it's a cartoon drawing, but it's pretty effective. You've got your cold molecules have less energy than your warmer molecules. And so the warmer it gets, the more energy it has, and the more movement it will have. In general, as you increase concentration, pressure, and temperature, all three of those will help increase your rate of reaction. Another thing that's going to affect reaction rate is concentration increase. It increases the rate due to the fact that there are more particles in a given volume, which creates more collisions. So if you look at the little picture here, over on the left, you've got low concentration. You've got low substance B. And so you can have some collisions and you can have some reactions, but when you dump more substance B into the solution, you've got a much greater chance that you're going to have more reactions. So the higher concentration is going to affect reaction rate by increasing it. Another way is surface area increase. And this increases the rate due to increased reactant interaction or collisions, or powder versus lump. Now I really like this picture because it shows you pretty definitively how chopping up a substance or breaking down a substance is going to increase its surface area. If you look at number 1 there, you've got this one block or your lump, and when you run the numbers, it gives you a surface area of 54 square inches. Then if you just break it into 8 pieces, it's going to increase it, and it's going to increase that surface area to 108 square inches. And then if you break it up even more, then you're all the way up to 162 square inches. That's a huge difference. I'll tell you a common example. If you've got a headache and you want it gone, you just say, okay, I'm going to take an aspirin. If you take an aspirin in its normal form, which is just the little pill form, which would be like surface area 1 example, it's going to react, but it's going to react kind of slowly, and it's probably going to take it about 30 minutes to kick in. But if you take that same pill and crush it up into powder and make it like picture 3 there, it's the same material. You increase the surface area by a great deal, and your body can access it and react with it that much faster. And you will really cut down on the reaction time of your body being able to use the medicine, and your headache will go away that much faster. The 5th way to increase reaction rate is to increase pressure. It increases the rate of reactions involving gases only. Now that's important. Remember that you're dealing with gases only. As pressure increases, the volume decreases, so the spaces between the molecules decrease, and the increased frequency of effective collisions. Now the reason this only works for gases is that gases are the only state of matter that are compressible. So it's not going to matter if you increase the air pressure around a solid or liquid. It's only going to deal with gases. A catalyst is a substance that increases the rate of reaction by providing a shorter or alternate pathway by lowering the activation energy of the reaction. Now, it's very important to remember or know that catalysts remain unchanged during the reaction and can be reused. The only time the catalyst is going to affect the reaction is when it's been put into the reaction scenario. The minute that it leaves, its effects stop. Activation energy, amount of energy required to start a reaction, and that's a review, but it's worth noting. So a quick review. Ionic solutions have faster reactions than molecular compounds, and that's because of the bonding. As you increase the temperature, you're going to increase the reaction rate. As you increase the concentration, you're going to increase the reaction rate. As you increase the surface area, you're going to increase the reaction rate. And this with gases, if you increase the pressure, you're going to increase the rate, and conversely, if you decrease the pressure, you're going to decrease the rate. And catalysts speed up reactions. Now, looking at a catalyst again, a catalyst is going to lower activation energy needed for a reaction, but it does not change the delta H value. And remember, the delta H value is the amount of energy that is either given off or absorbed. So, when you're looking at this, these are your activation energies. Up here, without the catalyst, it's pretty high. And then when you add the catalyst, you're getting rid of that much energy, which is a considerable amount. All right. Heat content or enthalpy is the amount of heat absorbed or released in a chemical reaction. And again, this should be a review for you, but in general, delta H is going to be products minus reactants. And remember, anytime you've got a delta, it's ending minus beginning. You've got a couple of diagrams here. Delta H is going to be positive when the reaction is endothermic. That's because the products are going to have more energy than the reactants. And then delta H is negative when the reaction is exothermic, and that's because the heat of reactants were greater than the products. So when you're looking at the picture down below that I creatively borrowed, you've got on the left, your reactants have more energy than the products. So over on the left, it's going to be a negative delta H because, again, you ended up releasing some energy. And then over on the right, that's going to be a positive delta H because your products ended up with more energy than they began with. Entropy. Entropy is defined as randomness or disorder in a sample of matter. Gases have the highest entropy, and then solids have low entropy, and you can see by the cartoon drawing there below that gases are going to have more movement and randomness than a solid would. If you're going to increase entropy, there are a few things that you can do. Number one, if phase changing from solid liquid to a gas is going to increase the amount of entropy. Mixing gases, different types of gases, is going to increase entropy, and so will dissolving a substance. So, there are several things that are going to affect reaction rate, and you need to make sure that you go through these notes and you know what they are, and you also need to make sure that you are very familiar with the vocabulary presented in this part of the notes. Next unit, or next video, we're going to be dealing with chemical equilibrium and what that entails, and kind of the intro to equilibrium. So until then, I hope you have a great day, and see you next time. Thanks.